So when we we were looking previously at oxidation and reduction reactions and predicting the products for oxidation and reduction reactions. So just as a refresher for some structures, we're looking at this example where we're asked to predict the products for the following reaction and draw a mechanism for the following reaction. In this case, we have a primary alcohol reacting with Desmartened Parietan. Now, just as a refresher to ensure that everyone's on the same page here, let's go back up and let's just refresh ourselves on the structure of Desmartened Parietan. So this is the structure for Desmartened Parietan. So let's just redraw that really quickly. So this is a classic hypervalent iodine reagent. Okay, and would anyone like to comment now that we have an idea of the structure of our reagent and our reactant? What happens when we treat primary alcohols with Desmartened Parietan? So Desmartened Parietan, what is special about this reagent compared to, for example, chromium trioxide conditions or a PCC oxidation? What's special about these reaction conditions? Would anyone like to provide a comment or input in the chat? So we're treating a primary alcohol with Desmartened Parietan. And what is the main use of Desmartened Parietan? So one student is commenting in the chat that it prefers to form an aldehyde, and that is a very important observation, a very important comment to note. Desmartened Parietan is very special in that rather than exhaustively oxidizing a primary alcohol up to a carboxylic acid, it's a very useful reagent for selective oxidation of a primary alcohol to an aldehyde. Now, the reason for this, if you notice, under the ambient reaction conditions, we're working under functionally neutral reaction conditions. So there's no large concentration of an external nucleophile. There's no sufficiently strong acid or base in solution. And that's very important to helping control this reaction and helping control the selectivity of this reaction to only oxidize our alcohol up to the aldehyde. Okay, so we have an idea about what's going to happen, and we have an idea that we would be able to isolate the following aldehyde from this primary alcohol. However, we have to be able to justify our predicted product, and we have to draw a mechanism that shows the conversion of our reactant to product. So, would anyone like now to try to annotate on the class whiteboard or to share a screenshot of their work on a separate piece of paper for the mechanism for this reaction? We've gone over the Desmartened Parietan oxidation mechanism in last class session. Would anyone like to showcase this mechanism or share their proposed mechanism for this reaction on the class whiteboard? Or would anyone like to comment, what's the first step in this reaction? How do we begin this oxidation mechanism?
Are we going to get rid of the hydrogen?
Sure, yes, eventually, yes.
Okay.
So we have a student commenting the Parietan will attack the oxygen. Yep. Parietan will attack the oxygen. What's the nucleophile in that case? The idea is good, but in terms of the phrasing, what's our nucleophile? What's our nucleophilic species? What's our electron-rich species? The alcohol or this Desmartened Parietan? The alcohol. So then our alcohol, which is our nucleophile, is going to attack our electrophile and displace an equivalent of acetate. Okay, that in turn okay, and now I'm going to draw out the acetate equivalence. Okay. So we're under neutral conditions. So the first step is attack of our alcohol. Now, in order for us to generate a neutral species, in order for us to sort of get rid of this relatively acidic proton, under the reaction conditions, it's very difficult for us to just have this protonated alcohol just floating around in solution. So in order to alleviate this issue and in order to generate an intermediate that can more readily undergo loss of hydride, what's the next step? So we have attack of our alcohol, and what's our next step? What's going to happen to this very acidic proton? What do we think now? Iodine doesn't leave in this case. So rather than iodine leaving, if iodine left, we would just go back to our reactant. What's another way that we can sort of get rid of this acidic proton? So we have an equivalent of acetate or solvent floating around, or even another reactant molecule. So what's going to happen next? How do we get rid of this acidic proton? Well, we can just remove it using a typical acid-base reaction, right? So acetate, it's a reasonably strong base. And this protonated alcohol is very acidic, so we can remove this acidic proton. Okay, that in turn gives us the following species. Okay, now I am drawing out this molecule in a very particular way to help highlight sort of the key step for this mechanism. Trying to get the geometry just right here, because we have our hydrogen. Okay, so I'm drawing out this structure somewhat provocatively, so that way we can easily draw out the key step for this Desmartened Parietan oxidation. One moment. Okay, perfect. So now we're ready for the actual oxidation step. And this is an intramolecular process. So in the end, we're going to need to remove an equivalent of hydride from our reactant. So would anyone like to draw out on the class whiteboard the arrow pushing mechanism for this step? Let me draw the acetate a little bit farther out so that way it's easier to draw the arrows. So how are we going to remove our equivalent of hydride and reduce our iodine from iodine 5 to iodine 3? Note this is an intramolecular reaction. And as another hint, we generate an equivalent of acetic acid as the byproduct. Would anyone like to propose the final oxidation step for this Desmartened Parietan oxidation? You can also share your responses in the chat or draw out the arrows on the class whiteboard. Would anyone like to propose the last step for this mechanism? Does anyone have a suggestion for the last step of the Desmartened Parietan oxidation mechanism? So, in order for us to go from this alcohol to this aldehyde, we're going to need to remove a hydride equivalent. The Desmartened oxidation is an intramolecular oxidative step where hydride is removed. Would someone like to, in addition to from referencing our earlier discussions of the Desmartened Parietan oxidation, would anyone like to try to draw on an arrow pushing mechanism for this reaction? So we're on the right, the general idea is good, but just to refine the arrow pushing mechanism, the acetate will pull off this hydride equivalent. We kick the electrons in this carbon-hydrogen bond to form our desired aldehyde carbonyl, and that kicks 2 electrons back to our iodine reagent. Simultaneously, we break the iodine-oxygen bond. So this frees up an equivalent of acetic acid and yields our desired product. This mechanism is found in the earlier pages of the chapter 17 note set. Does this mechanism make sense to everyone? And does everyone see that because we're using a relatively mild oxidizing agent, and because we're working under neutral conditions, this oxidation step will stop at the aldehyde. Does this example make sense to everyone? Any questions on this example? Notice in the end, we have an iodine 3 species. So we have reduced our oxidizing agent. Any other questions on this example? Any other questions on this example and the mechanism for the Desmartened Parietan oxidation? If we don't have any other questions on this example, let's look at a follow-up. So let's look at what happens when we take a primary alcohol, but this time we're subjecting it to chromium trioxide, oxidation conditions under acidic conditions. So if you have a primary alcohol, and you're oxidizing that primary alcohol under acidic conditions with chromium trioxide, what product would we expect to observe? What would we expect to observe? An aldehyde, an alkene, a carboxylic acid? What product would we expect to observe? Carboxylic acid, exactly right. Under exhaustive oxidation conditions, a primary alcohol will be oxidized sequentially up to the carboxylic acid. This goes through the intermediate aldehyde. Now, we discussed this mechanism as well last class session for chromium trioxide oxidations. So let's just show the structure for chromium trioxide. Would anyone like to volunteer? Let's take the next few minutes to work on this example. And would anyone like to volunteer and share a few steps of this mechanism? So this is going to take a few steps, so I'd like the class to contribute and help us advance our discussion through this problem. You can share your proposed mechanism as a screenshot of a piece of paper or OneNote screen as you draw out the mechanism, or you can also directly draw out your proposed mechanism on this class whiteboard. And I'd like to see some proposals for the mechanism. First, how do we get to this aldehyde? And second, how do we oxidize the aldehyde up to the carboxylic acid under acidic conditions? So what's the first step in this case?
Is the chromium gonna attack the oxygen? Yeah, the oxygen attack the chromium.
Yes. So
Yeah.
oxygen's a nucleophile, chromium's an electrophile. So we'll attack. That in turn gives us the following species. Now, from here, it wouldn't quite be correct to draw the oxidation step as an intramolecular process. So we have this protonated species. So in order to move our protons around to get a more workable intermediate, what's the next step? So how do we get an intermediate where we have a less acidic proton and we don't have this anion floating around under basic conditions? So we have to do a bit of a cleanup step where we move a proton around. Yeah, our base, which could be water or acetone, is going to pull off a proton. Yep. And at the same time, H3O plus is going to donate a proton. This serves two purposes. One, it activates our substrate. And two, it activates our chromium for the follow-up oxidation step. Okay, perfect. So now from here, what is the next step for this process? What is the next step for this process? So we need to oxidize up. We need to oxidize our substrate from this alcohol to an aldehyde. So we have to remove an equivalent of hydride. So how can we remove an equivalent of hydride? So just a refresher for the chromium trioxide mechanism. We've discussed this previously last class session, where after coordination, Chromium is reduced via abstraction of a hydrogen with base to give a ketone and a reduced chromium species. So, as a student has very astutely noted in the chat, that in this case, oops, sorry, one moment, let me get it set up. Sometimes there's a small delay when it's being streamed over. Okay, perfect. So then, in order for us to abstract an equivalent of hydride, our base, which can be water in this case, will pull off an equivalent of hydride, and we kick 2 electrons onto our chromium. So at the end of our first step, we have our intermediate aldehyde and our reduced chromium species. Now, unfortunately, it's very, very difficult to isolate the aldehyde under these conditions. The aldehyde is pretty reactive, and so it will be subject to further oxidation. So now that we have our aldehyde intermediate, how do we oxidize this aldehyde intermediate further? So most of these reagents function by pulling off an equivalent of hydride from an alcohol-like functionality. Now, we don't have an alcohol, but we can make a functionality with very similar characteristics to an alcohol. And to do that, we'd have to make either an acetal or a hemiacetal. So then, under acidic conditions, what's going to happen to our aldehyde under aqueous acidic conditions? What's the next step in this mechanism? So how do we generate an alcohol-like functionality? How do we generate a handle that our chromium can oxidize further? So we're not stopping at the aldehyde. Under these acidic conditions, in the presence of chromium trioxide, we're going to see further oxidation of our aldehyde. So what's the first step to generate a more reactive functional group handle? What's the first step for this subsequent exhaustive oxidation? So we have an aldehyde that's pretty electrophilic, and we're under aqueous acidic condition. Would anyone have a suggestion, or would anyone like to try to draw out this next step on the class whiteboard? Yep. Well, you can draw the first step as protonating the ketone. Okay. Sure, that's reasonable. Okay. So our carbonyl functionality in our aldehyde is now protonated. Okay. So now what? We now have a pretty active electrophile. We're in the presence of water, which is a relatively nucleophilic solvent. what's the next steps now? So you have water, which is a relatively nucleophilic solvent. So what's going to happen next? So to help everyone out for this key step, our nucleophilic solvent, which is water, is going to attack our electrophilic aldehyde. From there, that in turn gives us an alcohol equivalent. And then just for one more cleanup step, we're going to pull off our proton. So that in turn gives us the following functionality. And now we have a nucleophilic handle that can react further with our chromium trioxide. So, would anyone like to volunteer and showcase this next oxidation step with a second equivalent of chromium trioxide? Would anyone like to showcase this second oxidation step? So we have another alcohol functionality. We have chromium trioxide. So what's the next step? How do we oxidize our aldehyde up an additional time to the carboxylic acid? So as one of your classmates has noted, we have a nucleophilic functionality. We have this alcohol-like functionality, and it can attack our electrophilic chromium 3. Perfect. So I'll draw out that step just so that way everyone can see, and so that way it's saved in the class note set. Perfect. And now, just like before, we're doing a sequential oxidation. So we have our hydride equivalent. We have our chromium species. So what's the next step? What's the next step in this oxidation? So we have this protonated alcohol, right? And even though we are under acidic conditions, in order for us to activate our substrate for oxidation, what's the next step that we'd have to do? So what's our next cleanup step that we'd have to do in order to get a more workable species, in order to get something that can be more readily oxidized up? So we have a little bit of water floating around, right? We have water in this aqueous acidic solution. And exactly right, water can abstract a proton. Okay, perfect. So that in turn gives us the following intermediate. Okay, Okay, so now is our final step. So now is the final step in this mechanism. Let me just draw the water on the same line, so that way there are no issues here. So water pulls off a proton, great. Okay, so now what's the last step in this mechanism? What's the last step in this mechanism? We're almost there. How do we remove a hydride equivalent? So we're dealing with a chromium trioxide oxidation. What removes our hydride equivalent? What is going to pull off an equivalent of hydride in this case? So we have the hydride that we need to remove in this oxidation reaction. So what's going to pull off and remove an equivalent of hydride? How are we going to oxidize this substrate up to the carboxylic acid? So just like our first oxidation step, where we removed an equivalent of hydride to give our intermediate aldehyde, what's going to happen in this second oxidation step? What is going to remove an equivalent of hydride? Water, yep. Water or any sufficiently basic species will be able to pull off this equivalent of hydride that would then kick electrons down to generate the carbonyl for our carboxylic acid. And in turn, we kick 2 electrons to chromium to reduce the chromium trioxide down from chromium 6 to chromium 4. Okay, perfect. So that in turn gives us our desired carboxylic acid, which is the major product from this exhaustive oxidation sequence. We've covered this mechanism previously last class session. We were just doing a review on these common oxidation mechanisms, as you should be comfortable both predicting the products from these oxidation reactions and drawing mechanisms for each of the oxidation and reduction reactions covered in this chapter. Any questions on this example? If we don't have any other questions on this example, let's keep going now and let's begin our discussion, and let's talk a little bit about phenols and some reactions relating to phenols. So, phenols are generated by the ton. They're quite useful in resins and adhesives. Phenol is commercially generated via oxidation of isopropyl benzene and oxidation of other substituted benzene structures. Cumene is a common feedstock for this oxidative process, in which cumene is oxidized in the presence of air to cumene hydroperoxide, which under acidic conditions undergoes an alkyl shift to give phenol and acetone. These are quite important feedstocks that can be separated and are used as building blocks for subsequent industrial syntheses. So let's try to get a sense of the mechanism for this reaction. Let's try to rationalize the mechanism for this reaction. So first and foremost, when we start off with isopropyl benzene, we have a highly activated benzylic hydrogen. This benzylic hydrogen can be readily abstracted to yield a highly stable tertiary benzylic radical. That radical can then combine with oxygen to generate the corresponding hydroperoxide. So, one question I have for the class is, what makes this oxidation reaction occur so readily? What makes this radical oxidation occur so easily? What's the important thing to note here? What's really special about this substrate and the radical generated from this substrate? Would we consider this a stable radical or an unstable radical? Would we expect this radical to be easy or difficult to generate as well? What do we think? So a tertiary benzylic radical. Would we expect that to be a stable or unstable radical? Very stable. And that helps explain why this reaction occurs so readily. Now, to continue on the chain, we can just as easily abstract a hydrogen, and that in turn gives us our hydroperoxide. Now from there, once we've made our hydroperoxide, this substrate in the presence of acid undergoes a pretty interesting decomposition reaction involving an alkyl shift. So in the first step, we protonate our alcohol oxygen, or in this case, we protonate one of the hydroperoxide oxygens. This generates an activated leaving group. From there, we have an alkyl shift. Part of the driver, one of the main driving factors behind this alkyl shift is that we lose a highly activated leaving group, in this case, water, and we generate a very stable tertiary carbocation. From there, an additional equivalent of water can attack our tertiary carbocation. And from here, we have to do a quick proton transfer in order to set our substrate up for the second step. So first, we protonate one of our alcohols and we deprotonate the other alcohol. Okay, now from here, this intermediate known as a hemiacetal is not particularly stable. We'll see these a lot more in chapter 20. And these hemiacetals, just like the intermediates that we've seen time and time again when we dealt with addition of Grignards into carboxylic acids, for example, these intermediates where you have a tetrahedral intermediate with a leaving group present. In this case, your leaving group is an alkoxide leaving group. In this case, we can readily and quite easily just collapse down our tetrahedral intermediate and kick out our leaving group. And that's exactly what happens here. Our hemiacetal intermediate collapses and we generate our ketone, acetone, and our alcohol, phenol. Does this mechanism make sense to everyone? Do the steps for this mechanism, both for the oxidation of isopropyl benzene to yield our hydroperoxide and then the decomposition and rearrangement of our hydroperoxide under acidic conditions to yield phenol and acetone. Does this mechanism make sense? Any questions on this mechanism? Okay. So if we don't have any other questions, let's talk about some interesting reactions of phenols. So we know that phenols as substrates contain a very strong activating group that activates the ortho and para positions. The hydroxyl group is a strongly activating ortho-para director. And so phenols are highly reactive substrates for halogenation, nitration, sulfonation, and Friedel-Crafts reactions. An interesting, unique reaction of phenols is that they can be oxidized up to a quinone under treatment with either sodium dichromate or Fremies salt. Now, in both cases, this allows us to generate a quinone, which can then be further reacted and further derivatized. So for example, from here, you can then treat it with a Grignard reagent. You can treat it with, for example, an amine to make an imine, which we'll see in subsequent chapters. So this quinone is a pretty reactive subunit that can be derivatized using a range of different reactions. And what's really interesting, and we'll talk about this in later chapters, is you can take a quinone and treat it with like an alkyl copper or alkyl cuprate species, and you can install an alkyl group. And the beautiful thing about phenols is that when you attack a phenol, you generate an intermediate that is very close to reaching aromaticity. And all it takes is just a quick tautomerization step. And we're back to a substituted phenol. So there are two things that this oxidative process is useful for. One, generating substituted phenols, and two, for installing oxygen or alcohol functionalities at the para position relative to a phenol alcohol. So you'll see very similar oxidative processes used when you're dealing with these quinone systems, or when you want to make a quinone, or when you want to make a highly substituted phenol. This is just another unique tool and a unique pattern of reactivity that phenols can be subjected to. Does this make sense to everyone so far? Okay, so let's keep going then. So what we're going to do now is we're going to integrate the strategies that we learned in the chapter portion on oxidation and reduction with the strategies that we've developed for making substituted alcohols, ketones and carboxylic acids through the use of Grignard reagents and other reactions. So what I want us to do now is I'd like us to take a look at this substrate and let's try to think of a reasonable retrosynthesis and forward synthesis. Now, there are two tools that we can use at our disposal. The first tool is an FGI, or functional group interconversion. This is one retrosynthetic step that we can utilize. A classic example of this is tracing back ketones to the corresponding alcohol. We can make ketones from the alcohol via oxidation. Okay. The second example is a bond forming or bond breaking transform. And examples of this would be making a substituted alcohol via Grignard addition into an aldehyde. In each case, what I want you really to think about in your retrosynthesis is what patterns of reactivity do I need? And is there a way that we can look at our substrate and think about how the bonds are connected in our target molecule that would allow us to create reasonable fragments? So the first place I always start when I'm planning a retrosynthesis is I look at the distribution of electron density in my molecule as is. So as currently drawn, we have a very electron deficient carbon, and the carbons adjacent to a ketone are typically viewed as relatively electron rich and can serve as nucleophilic functionalities. Now, this pattern is known as a consonant pattern, and it follows the typical sort of drawn and apparent distribution of electron density in your molecule. The carbon attached to a carbonyl is typically electron deficient. And when we think about bond forming or bond breaking transforms, if we wanted to prepare this asymmetrically substituted ketone, it would be reasonable for us then to think about how we can break bonds around this ketone. So with that said, would anyone like to propose a functional group interconversion or a bond forming or bond breaking transform? How are we going to go about preparing this molecule from fragments that are 6 carbons or less? So 6 carbons or less is our limit. So which bond would we like to break, or what bond would appear reasonable to break? So let's take a few moments and let's try to use the annotate tool to showcase what bond are we going to break, what synthons are we going to then draw out, and what actual fragments are we going to use to prepare this molecule. This synthesis may take you a few steps. It may take, rather than just one step, it may take a total of 2 steps to complete. So would anyone like to annotate on the class whiteboard? Which bond would you prefer to break? Okay, so we have a student proposing that they'd break this bond. The student's probably thinking that, well, we have a 6 carbon fragment here. So if we wanted to simplify and get to fragments that have the minimal number of carbon atoms, this is a perfectly reasonable bond to break, as it simplifies our structure dramatically. Okay, so now that we propose breaking that bond, so we're breaking this carbon-carbon bond, we'll call this option A. When we break this bond, what synthons then would we be working with? What pattern, what distribution of electron density would we need on each of our two fragments, each of our two reactants, in order to form this desired bond? So what is our go-to method of forming carbon-carbon bonds in this case? So what would our synthons look like? For the student that showed this bond breaking step, would you be able to draw out our two synthons? And considering that we drew out a consonant pattern here just to get a sense of, well, how can we form our desired bonds? What bonds look reasonable to break? So in terms of synthons, we draw out our two fragments after breaking the indicated bond, and we think, where are we going to place our electron density? Which carbon will be electron rich and which carbon will be electron deficient? So we have a student drawing out an aldehyde, and what's the other proposed fragment? So we have an aldehyde. This is an electron deficient fragment, an electrophilic fragment. And what's our nucleophilic fragment? How are we going to form this desired carbon-carbon bond? What is our other fragment going to look like? Would the student like to draw out the second fragment and complete the second fragment so we can talk about this as a class? Or would anyone in the class, oh, a Grignard, yep. So someone in the chat mentioned a Grignard, that's a great idea. So that's our nucleophilic fragment. Okay, so I'm gonna clear this proposal, and we have to unpack something, because although this proposal is very good and it's actually quite reasonable, there's one thing I'd like us to note when we draw synthons and fragments. So first, in terms of synthons, just in general, we have a few options, but the first of which is to put our nucleophilic fragment, to put our negative charge on our cyclohexane fragment, and to put our positive charge on our carbonyl or ketone-like fragment. Okay, now the reason why I have you draw these, synthons out is because they allow you to think about many possible fragments that would match the desired distribution of electron density needed for an efficient reaction. So when we look at the oxidation number of this carbon atom in this case, we see we have an oxidation number of +3. This reminds us a lot of the carboxylic acid or ester oxidation state, right? Does everyone see how this carbon has an oxidation number of +3? Now, when the student went to convert these synthons into fragments, I found it really interesting that they decided to go to an aldehyde functionality. Now, the reason why that's so interesting and why that was a very good strategic move has to do with chemoselectivity. So to showcase the students' thought process, they went to this first set of synthons and then this second revised set of synthons, where in this case we have an oxidation number of +1. It's important that you pay attention to oxidation numbers because in effect, the student implicitly wrote a functional group interconversion. Does everyone see how these two oxidation numbers are different? Does everyone see how these two oxidation numbers are different? +3 and +1 are different. So let's look at what happens if we convert each of these synthons into appropriate fragments. So in the first case, our nucleophilic cyclohexane fragment will just be a Grignard cyclohexyl magnesium bromide. Super easy to buy, super easy to make, no big deal. Now, in terms of this acyl fragment, my question to all of you is, we're either in the oxidation state for a carboxylic acid, an ester, or an amide. Which functionality would be most appropriate if we're dealing with a Grignard reaction? If we're using a Grignard, which functionality would be more appropriate? What would we prefer? Let's just talk as a class. An ester or a carboxylic acid? Which functionality should we draw if we wanted to get an efficient bond-forming reaction? The ester would be better, yep. And we can just draw this as the methyl ester. Unless there's a reason to, there's no need to make the ester anything other than a methyl ester. We'll talk about some reactions that prefer different types of ester functionalities, but generally the methyl ester will work great for Grignard additions. Now, what's a problem with the carboxylic acid? What's a problem with the carboxylic acid? And it brings up this idea of chemoselectivity. What's the problem with using a carboxylic acid in this case? Why don't we propose, so I have one student commenting in the chat, the hydrogen. That's exactly right. The carboxylic acid functionality is acidic. And acidic functional groups, such as alcohols and carboxylic acids, are incompatible with Grignards. So the reason why we go through this list of possible options and we deliberately pick our preferred fragment that matches this synthon is because we want to be able to consider and really think through the chemoselectivity. Grignards do not react efficiently and do not react to give the desired carbon-carbon bond-forming reaction if you have an acidic functional group. Okay, perfect, perfect. Now, this first pass idea, Grignard and ester, if we run this reaction, do we get out our desired product? If we run this reaction between a Grignard and a Grignard and an ester, do we observe the desired product? Would we get this ketone out cleanly? So if we have a Grignard and an ester and we mix them together, what is the textbook pattern of reactivity when you have a Grignard and an ester? Do you observe monoaddition? Are you very likely to get a ketone out from this reaction? So if you mix your Grignard and your ester together, would you expect to isolate this ketone cleanly? would we be able to isolate this ketone with no issues? So I have one student commenting you'd end up with 2 cyclohexyl groups attached. That's exactly right. Remember, when you react a Grignard and an ester, the first addition occurs and we generate the ketone. The second addition then occurs on the activated ketone to generate a highly substituted tertiary alcohol. Remember when we did a previous synthesis example, we saw that a wonderful way to make a symmetrically substituted tertiary alcohol is through addition of a Grignard into an ester, because 2 equivalents of Grignard will add into the ester. Does that idea make sense to everyone? So this first route would not work. We don't observe the desired chemoselectivity. So what are we to do then? Well, we have another option. We have another proposal. And that is, we can still go through a Grignard, but let's go through a different carbon oxidation state. So in this case, we have a fragment with an oxidation number of 1. And this brings us back to the student's main idea, which is to use an aldehyde instead. Okay, that is fine. However, and this is really important, if we use an aldehyde, or if we use a different carbon oxidation state, we'd make a fundamentally different product. To get these fragments, rather than having a ketone, we'd be making an alcohol. So this is a classic example where we use a functional group interconversion to trace our substrate back to a different oxidation state or a different functionality that is easier to make, right? It's much easier to make this alcohol, right? It's pretty easy to make this alcohol, would we all agree? Or currently we have a route that would make this alcohol, right? And by going through the alcohol, we can sidestep this chemoselectivity issue associated with our ester functionality and associated with trying to make this ketone directly. So from here, now that we have this alcohol, we're breaking the same bond. That allows us to trace back to this nucleophilic and this electrophilic fragment. And the student astutely noted that our 2 fragments as drawn closely match the cyclohexyl magnesium bromide Grignard reagent and butanol, which is a 4-carbon aldehyde. Now, if we mix this Grignard and this aldehyde together, what product would we observe? What product would we observe? So now we're dealing with our forward synthesis. We've gone from our synthons to our fragments, and now we're tracing out our forward route. So what would we get when we mix this Grignard and aldehyde together? What product would we get? So we previously proposed a synthesis. We're aiming to prepare this ketone, right? We focused on breaking this indicated bond as it would give us the simplest fragments. We entertained the idea of making this ketone directly, and we found a chemoselectivity issue. So instead, we decided to change the oxidation state of this carbon to that of an alcohol. From there, we got the following two synthons as drawn by the student, and those synthons match that of an aldehyde fragment and a Grignard. So, if we mix this aldehyde and Grignard together, what product would we observe? Would the student or another student in this class like to continue on with this process, like to help advance our discussion? So we've drawn out our fragments, we've drawn out our reactants, and now from thinking about this synthesis in a forward direction, if we mix our Grignard and our aldehyde, what product would we get? Would anyone like to try drawing the product, drawing an arrow pushing mechanism for what will occur in this drawn reaction? Or would anyone like to share in the chat what product would we see from this step? Yep, exactly right. Our Grignard will attack our aldehyde and we get the alcohol that we drew out when we were planning our retrosynthesis. Yep, exactly right. Perfect. So as drawn, we would be able to easily make our desired secondary alcohol by mixing our Grignard and aldehyde and then quenching with acid. So we would be able to pretty easily make this substituted secondary alcohol. However, and this is really important to think about, if our goal is to make a ketone, how do we take this alcohol? How do we take this alcohol and complete our functional group interconversion? How do we make a ketone from an alcohol? What conditions would we use to accomplish that? What conditions would we use to accomplish this reaction or to accomplish and complete our synthesis? So if we want to take this alcohol, which we can easily make, and convert it to our desired ketone, treatment with base would just deprotonate it. How do we go from an alcohol to a ketone? What conditions do we need to utilize? So how do we accomplish this functional group interconversion? How do we go from our alcohol to our ketone? Have we discussed conditions and reactions that allow us to convert an alcohol to a ketone? What conditions would work for this transformation? Would anyone like to share a proposal in the chat or verbally? So just to recap once again, we noted that accessing this ketone oxidation state directly was difficult. So we did a functional group interconversion between a ketone and an alcohol retrosynthetically. We then traced back this alcohol to our Grignard and aldehyde fragments. So my question to everyone is, now that we've have a forward synthesis to get to this secondary alcohol, how do we go from this alcohol to the ketone? Yep, any oxidation would do the trick. Desmartened Parietan, yep, that would certainly do the trick. You can also do a chromium trioxide oxidation. You can also do an oxidation with PCC. All of those would work. So this is a generic oxidation. So we can oxidize our alcohol up to the ketone, and that would complete our synthesis. The central idea behind this retrosynthesis example is this idea that you can utilize functional group interconversion involving oxidation and involving reduction in order to allow you to control the chemoselectivity. It's very difficult to directly generate our ketone due to this chemoselectivity issue. However, we can easily make the alcohol and then oxidize that alcohol up. So you should be aware and you should think about these functional group interconversions. You should think about oxidation and reduction as tools to plan your synthesis and retrosynthesis. So the student comments and the student proposals were very helpful in this example. And the proposal to use an aldehyde was quite an insightful proposal because it recognized and it avoided a major issue in chemoselectivity. The one thing I want everyone to be aware of is that when you think about using fragments with a different oxidation state than your synthons, you will need to do a functional group interconversion at some point in your synthesis, be it an oxidation or a reduction step. Does that idea make sense? And does this example make sense? Does the thought process behind this example make sense? Any questions I can address? Yep, exactly right. And it's important to recognize changes in oxidation state. And you should incorporate these oxidation and reduction reactions into your synthesis planning, because in some cases it can save you a lot of trouble in chemoselectivity. Any other questions or comments on this example? Okay. So let's look at another case where we have to utilize reactions that we've learned in this chapter, be it use of protecting groups, oxidation, reduction, and use of Grignards as reagents to form carbon-carbon bonds. And let's try to propose a synthesis of the following molecule from fragments that are 6 carbons or less. So let's take a moment and let's look at this structure, and let's try to identify. First, I'll show the consonant pattern. So there are 2 potential consonant patterns to work with. We can either start counting from this alcohol carbon on the right, or we can start counting from the alcohol carbon on the left. You may notice that in this case, our alcohols are arranged in a way where we have a conflicting assignment of our electron density that we'd want to form a bond and the electron density as distributed in our actual molecule. We call this pattern a dissonant pattern. And in many cases, this means you may have to use a bond forming step that uses polarity reversal, or you may need to be a little bit careful with which bonds you break. So I'd like us to take a look at this structure. I've drawn out both of the electron distribution patterns that we could draw from each of our 2 alcohol functionalities. And I'd like us to think, what bonds can we break that would give us fragments that are 6 carbons or less? And I would really try to identify what bond, when broken, would give us the simplest fragments. So, does anyone have a proposal? Which bond would we like to break? Or does anyone have a proposal that would require a functional group interconversion? So we see a student propose breaking the following carbon-carbon bond. And that's quite a simplifying disconnection. As you can see, if we break this bond, we get 2 fragments each that are 6 carbons each. Wonderful. Okay. From there, now that we've drawn out a bond forming or bond breaking transform, what would our synthons look like? Let's start to think, how would we go about forming that bond? How would we go about forming that bond? So what would our synthons look like? Or you can draw the fragments if you're more comfortable drawing the fragments directly. Interesting, really interesting for these synthons. The synthons look good. Is that an OH or an OR group? And this is a very important point. Oh, okay. Okay. So let me redraw the synthons. Let me redraw these synthons. And now let's think as a class, what fragments would match? What fragments would match these synthons? So what actually isolable and practical species can we use to match and that can be used with the same reactivity and distribution of electron density as these synthons? So what fragments are we going to use that match these synthons? So we have one student commenting in the chat, the alcohol on the left would need to be protected somehow. That is a very astute observation. Would we be able to draw out a draft for these fragments? Let's just draw out a first draft for our fragments. What reactants would we use to match these synthons? What reactants would we use to match these synthons? So we have a carbon with an oxidation number of +1. What does that remind us of? So this fragment on the right, we have an electrophilic carbon with an oxidation number of +1. What kind of fragment, what kind of reactant does that remind us of? Let's take a moment and we have one student commenting an aldehyde. Okay, so let's draw an aldehyde. Yep, has the same oxidation state. We have a very electrophilic carbon. Perfect for carbon-carbon bond forming reactions. Okay. What matches this nucleophilic synthon? What matches this nucleophile? What's a nucleophilic fragment that we've used time and time again in this chapter? What would be a reasonable reactant for our nucleophile? A Grignard, yep. Okay, so let's draw. Now, let's just take a moment and let's really take in what we're implying here. So in our discussion of Grignards, is it very easy? Is it very straightforward to make a Grignard when you have an alcohol functionality already present? Is this Grignard isolable? Can we actually make this Grignard as drawn? No, that's correct. We can't. However, and this is important to consider, is there a way for us to mask the reactivity of this alcohol? Is there a way for us to hide our alcohol so that we can make our Grignard, perform our desired bond-forming reaction, and then free up our alcohol later on in the synthesis? Is there a tool that we have to mask our alcohol functionality? We can protect it. Exactly right. Exactly right. So then, this is another type of functional group interconversion. So I'm going to call this is another FGI, where rather than trying to directly make this diol, instead, what we're going to do is we'll make a protected alcohol. From here, we can break the same bond and trace this back to a nucleophilic fragment, except this time our alcohol is protected. Now, why is that a big deal? Well, if the alcohol is protected, suddenly our issue of side reactions and making our Grignard is no longer an issue. So, can we make this new fragment now? Can we make this fragment? Is this easier to make? Can we actually synthesize this protected fragment? Or more specifically, can we make this Grignard? Is this Grignard reasonable to make? Sure. Yeah, for sure. The alcohol is protected. We won't end up protonating and quenching our Grignard. So this is a perfectly reasonable Grignard to use. However, unfortunately, we're not quite done because a trimethylsilyl group, trimethylsilyl, as the name implies, this fragment as drawn has more than 6 carbons. So we're going to have to continue on with our retrosynthesis. So we can make this Grignard from the bromide, right? That's easy. And where do we get this protected alcohol from? And really don't think about this question. It's not a trick question. Where do we get a protected alcohol from? So where can we trace back a protected alcohol to? So we have a protected alcohol, and where do we get that protected alcohol from? And it's not a trick question. Through installation of a protecting group. And what's our reactant? Where do we get this protected alcohol from? From an alcohol. Exactly. Okay, perfect. So we can trace it back to the following substrate, which is pretty easy to make, but we can buy it. It's 6 carbons or less, and it meets all the criteria. Okay, does everyone understand the logic for this retrosynthesis? We need to use a protecting group to avoid side reactions and to avoid quenching our Grignard. A Grignard is incompatible with a free alcohol, so we have to protect the alcohol in order to make our Grignard. Does that idea make sense? Yes, and it was more than 6 carbons because a TMS group has 3 carbons on it, right? So it's always important to remember the structure of your protecting groups and of all these groups with nice abbreviations, because a TMS group, a TOSL group, they're not just acronyms, they have defined structures. So if I say make it from a fragment that's 6 carbons or less, you need to make sure the TMS group is off unless you have a very small fragment. Does that make sense? Okay, so this is retrosynthesis. So we're tracing back our desired product to these simple fragments. So now for our forward route, we're going to trace our fragments through step by step. So here we go. So we have our alcohol. So our first step is to make our protected alcohol. So what conditions do we use for installation of a TMS group? What explicit conditions would we need to use? How do we go from an alcohol to a protected alcohol? What conditions would we need? And don't be shy to flip to the earlier section of the notes on alcohol protection, but I'd just like the class to contribute so that we can trace from start to finish. So we showed our retrosynthesis, we worked through the retrosynthesis. Now let's think about the forward synthesis. We're just tracing our steps back. So what conditions do we need to protect an alcohol with a trimethylsilyl group? Would anyone like to type the conditions in the chat or share their proposed conditions verbally? So how would we install this TMS protecting group? How would we install the trimethylsilyl protecting group? Sure, but what exact conditions would we need? What reagents would we add above this reaction arrow? What reagents would we need to add in order to install our trimethylsilyl group? So we have a student commenting the oxygen would attack the trimethylsilyl group and the hydrogen would need to be removed. Yes, that's what's occurring mechanistically. But what conditions would we need? What reagents would we need to add? So to install a TMS group, we need to use trimethylsilyl chloride and a base, either triethylamine or Parietan. So that will allow us to protect our alcohol. Now, we're dealing with a Grignard reaction between a Grignard and an aldehyde. So how do we make our Grignard? So we have our aldehyde ready to go, and we're going to add our aldehyde once we make our Grignard. What do we use to make a Grignard? What exact conditions do we need to make a Grignard? What reagents? How do we make a Grignard from an alkyl halide? Magnesium, yep. And what solvent? Ether, typically. The student comment about a non-polar protic solvent, that would likely destroy the Grignard pretty quickly. Generally, Grignards work best with ethereal solvents like diethyl ether. You can use THF as well, but diethyl ether is the most common by far, though tetrahydrofuran is also an acceptable answer. Okay, so we make our Grignard. So we've checked that box. We have our aldehyde, and we can just buy it since it's 6 carbons. Okay. And just as a final note, at the end of our reaction, we need to quench our Grignard and quench the alkoxide generated from this Grignard addition. Okay, so that gives us the following product. Now, one thing that I would like you to be somewhat attentive to is this idea of one step serving multiple purposes. So what's so special about quenching with acid, and what's uniquely useful about quenching with acid? Does everyone notice a pretty important point in this sequence? Our quench step doesn't just quench the alkoxide. What does this quench step serve to do? Just in general, if you have a TMS group and you treat it with aqueous acid, what happens to the TMS group? It removes the TMS group, yep. Acidic conditions are textbook conditions to deprotect a trimethylsilyl group. If you really wanted to, what's another way to deprotect a TMS group? If our acid quench didn't do the trick, what's another way to get rid of this TMS group? That is not hydrofluoric acid, just to put a limitation for practicality. What's another way to get rid of a TMS group? What's another textbook reagent that we could use to deprotect the TMS group? Besides acidic conditions, what's another way? Just for your reference, another way to remove a TMS group is to use TBAF, tetrabutyl ammonium fluoride, which deprotects our TMS group because fluoride reagents can form a pretty strong silicon-fluorine bond and can nucleophilically displace our alcohol. Okay, so the two takeaways from this example. One, well, this was discussed earlier on in the chapter when we talked about TMS protection. The main point I want that everyone to notice is this idea that these protection and deprotection reactions have a purpose. They're used as part of synthetic planning to enforce chemoselectivity and minimize undesired reactions. So when you think about planning a synthesis, when you think about predicting the products from a reaction, it's important to have these protection, deprotection, oxidation, and reduction reactions at your disposal because they're invaluable in enforcing chemoselectivity and planning a synthesis that would actually give you the desired product. Does that idea make sense? Do these examples make sense to everyone? So as you can see, these are 1 to 2 step syntheses using reactions that we've covered throughout this chapter. And it really shows you the power of these simple reactions to make pretty complicated molecules. So, any other questions on this chapter? So we've reached the end of chapter 17. Any other questions? Okay, at the end of this chapter, I've also posted a sheet that reviews the spectroscopy of alcohols and phenols. It's an exact copy from the chapter 13 note sets on IR spectroscopy, but I just included this summary that directly relates to alcohols and phenols for your reference. Any other questions I can address before we close out our lecture on this chapter? If not, we'll archive this recording